Hello and welcome to the second part of the path tracing lecture. My name is Adam Zellerek. Let's have a short overview first. In the last part, we saw some basics of the path tracing algorithm. We've seen materials, the path tracing algorithm itself, and how to optimize it using next event estimation and Russian roulette. Today, we will see some more details. For instance, how to filter the signal, how to parallelize the work, measure error, and some post-processing. We start with filtering, the goal of which is to reduce or prevent sampling artifacts, or in other words, aliasing. And by the way, that picture is from Finland, the home of some very good computer graphics people. We begin with an example. On the left, filtering was used, and on the right, not. The left looks a bit better when you compare these areas and here at the bottom. We can zoom in to see the difference more clearly. There are these bright pixels here and here in high frequency areas that clearly go away when we filter. We have to look into it. Let me give some context about where filtering happens. It is applied in the image coordinate system where we see the pixels. That means that it lives in the main rendering loop where we walk over pixels, in contrast to where we lived in the first part of the path tracing lecture, the recursive part. In case you are taking the course at TU Wien, you implemented the box filter for assignment 2. That is, you chose random samples inside each pixel and computed the average as an estimate of the pixel color. That is already filtering. But in order to make the explanation simpler, let's go a step back for now and use only a sampling position in the pixel center. In fact, this will be probably the way we will teach Monte Carlo next year. We'll forget about one of these green dimensions and start to think about a 1D function f of x. This is to make the explanation easier. All of the results also apply to the 2D screen we have in rendering. The green wavy line, in here and in here, is now the function that we want to sample and reconstruct as pixels on the screen. In here are pixels, and in here we have the discrete version of pixels in 1D. So f of x is the integral over the light transport function over all transport paths. This is the path integral formulation, and I used it here because it's shorter. You already learned in the first part of this lecture how to estimate the results using Monte Carlo. It's the same process, no matter the notation. But we can also use the recursive formulation. In that case, we would say that we have a function f that eats screen coordinates. The definition of the function tells to shoot a ray through that position and compute the light recursively. That recursive computation returns the brightness at that position of the screen. For now, we assume that f of x is a continuous function, as opposed to a stochastic variable like in Monte Carlo integration. That means that it always returns the same value for a given position, and positions are not discrete like monitor pixels. Now, we have that function f, but only discrete pixels in here, where each of them can display a single value. This is a sampling problem, very much like when you have to convert an analog audio signal to a digital signal and then play it. Let's say we go the simple and naive way and sample the signal at the centers of the pixels. In here and in here, you can see the sampling positions in here. After sampling, we have to reconstruct the signal, that is, draw it on the screen. As said, every pixel can have only one value, hence the boxier reconstruction. This gives us a faithful representation of f if the frequency is low. By faithful, I mean that the pixel values are close to the signal f, and that they would not change much if we shift the sample position a tiny bit to the left or a tiny bit to the right. Sampling the pixel centers works if the signal f has a low frequency, but it breaks down when the frequency becomes larger, like you can see here on the right. The problem is called aliasing. You probably already heard about it. It happens when the sampling frequency is below the Nyquist frequency, which is 2 times the signal frequency. There are 2 solutions: increase the sampling frequency or smooth the signal. We can't really do the first because it would change the rendering resolution. Besides, when would we stop? But we can smooth the signal. Smoothing the signal means to apply a low-pass filter, H. We are filtering out high frequencies, hence the name of this section. Look at that. If we sample the yellow signal, which is F convoluted with H, at the centers of the pixels, it will give us faithful values to be used for reconstruction as a pixel signal. You might think that we lose data, but that is not really the case, as we couldn't reproduce it anyways. Let's look now into choices for the filter, or convolution kernel H. First, we have to look at the properties that we need. It should integrate to 1. This is because f of x convoluted with h of x should not be brighter or darker than the original signal. This is more of a theoretical constraint, as any convolution kernel can be scaled, and in fact we do that as part of the equation that we will see and use later. Obviously, the kernel shouldn't be too small or too large. In the first case, we wouldn't fix the reconstruction problem, or in the second case, we would lose too much detail. And finally, we need a good shape. Depending on the shape, some artifacts might appear. Different shapes can create different artifacts, and it's generally a trade-off between these artifacts. But we won't go into much detail here, because we would need much more sampling and reconstruction theory, including the Fourier transform. And I'm not going there, not this time. Here we see some choices for the kernels. The first row is the 1D case and the cross-section through the centers of this 2D case at the same time. The simplest is the box filter, which is super simple to implement. You just take the average of all pixel samples. We'll talk more about how to implement later. It is common in super simple renderers, in case the author is too lazy to implement something better. It allows high-frequency sample data to leak into the reconstruction, as stated in our course book, Physically Based Rendering. The 10 filter is slightly better, and the Gaussian filter is reasonably good, but smooths the result. As you see, the Gaussian is clamped in here and in here. This is to limit its support. There is a family of filters called Mitchell-Netrevally. You can see that they can be negative in here and in here. This sharpens the result somewhat, but can cause an artifact-caused ringing, and this depends on the parameters. The Mitchell-Netrevally filter is considered the best by some, and I think it is a bonus task in assignment 3. Anyway, we will not go into further details or differences. In my opinion, they are minute between Gaussian and Mitchell-Netrevally. Okay, we have seen why. We have seen the filters, but not how that works in the context of rendering. So here we go. You see the signal F and the filter kernel H. Before, we said that we compute the convolution between F and H in order to get a smooth signal. But we do not have the signal F as a function. We can only sample it. And so we need to change the approach somewhat. We see that the center of the filter is placed over the current pixel. This is like we wanted to compute the value of F convoluted with H at this position. And now we take samples of F times the filter H. Samples close to the pixel center will have a larger contribution than samples away from the pixel center. Here you see the equation for that process. In the numerator you see exactly what we said before. The sample values of F are multiplied with the value of the kernel, which is centered at the pixel center. The pixel center is this X. This is the same as convolution. Remember, we said that h should integrate to 1, so in theory we would not need the normalization in the denominator in here, as it would add up to n on average. However, using it reduces noise. And here you see the equation for the 2D case that we actually have in case of rendering. It works the same way. Now, let's have a graphical view of that kernel again. The green circle is the filter. The red dots in here are the samples of the current pixel. The filter kernel is larger than the current pixel. And so pixel samples also contribute to neighboring pixels. As you can see in here, these samples also contribute to that pixel, or samples in here would also contribute to that pixel. The number of neighboring pixels that we need to look at depends on the filtering size. Okay, I hope that is more or less clear, and we are ready to look at another thing concerning filters. Many discrete smoothing filters are separable. That means that the matrix of the filter can be computed as the outer product of two vectors. This applies, for instance, to the Gaussian, the Tent, the Box, and the Mitchell natural value filters. And since these filters are symmetric, the two vectors have the same values. Separability allows us to implement filters more efficiently, as we need to store only one vector instead of the whole matrix. The filter values can be computed on the fly. In case you work on assignment 3 at TU Wien, this is the code that you have to complete. Alright, we learned that filtering fixes aliasing problems, low-pass filters are used, and the process includes convolution and normalization. Most filters are larger than a single pixel, and so most samples affect more than a single pixel. Here are some reading links. Check, for instance, our course book. It covers sampling and reconstruction quite extensively, including more sampling theory and comparisons between the different filter types. A classic read is "A pixel is not a little square." You can also read the original paper by Mitchell and Nettevalli. And finally, I've seen that there are many YouTube videos about sampling theory, and probably at least as many resources on the internet. That concludes our section about filtering, although we will see it again in the next section. Filtering prevents or at least reduces sampling artifacts by low passing the image signal and then sampling in the pixel centers. These samples are then used as the pixel color. And now let's have a quick look at parallelization. The goal is clearly to harvest the performance of modern multi-core systems. That is already crucial today, but it becomes more and more important as the core counts increase. By the way, if you read papers from the 90s, that won't be the case. And by the way too, this picture is also from Finland. The summers there are amazing. Monte Carlo rendering is embarrassingly parallel, as every sample of the integrand is independent. We are talking about the paths that start or end at the camera, not the hemisphere samples. So we could start a new thread for each sample, but that would require synchronization at the sum and probably unneeded overhead for threading. That might pay off for GPUs, but probably not even that, certainly not for CPUs. We could start a new thread per pixel, but this is more GPU style. For the CPU, that is still too much overhead. Plus, we would actually need synchronization because of overlapping pixel filters, but that is doable. So for CPUs, we use blocks of pixels. Such blocks can have a size of, for instance, 32 × 32 pixels. Another advantage is that the first few bounces will have a high probability of hitting the same geometry, and so the caches of the CPU have fewer misses. Blocks at the border of the image are often smaller. Samples are taken for all pixels inside the block, but as said, due to filtering, each sample can contribute to more than one pixel, including pixels outside the block. Therefore, each block needs an additional border to store that contribution. And so, when a block is handed to a thread, it must be slightly larger than the extent of the sampling area. This means that blocks can overlap. We will now see how that is handled in a rendering system like Nori. When we look back at the equation for filtering, we see that there is a sum in the numerator and the denominator. We have to complete the sum before the division. That means that we need to do the division after merging the blocks to the complete image. And that is actually quite easy. We just keep track of the numerator and the denominator separately. Then we add the blocks to the final image using blocking or atomic add operations. And finally, we do the division once all threads are finished. Nori solves that by putting the three values of the numerator for the three colors and the filtering weight into a 4-element vector. The blocking add operation doesn't even need to know what the data is. As a last step, we simply divide all pixels by their fourth component. That was done in TU Wien's second assignment. For path tracing, we can use this method without any problems, but some other algorithms require access to the whole image. For instance, that would be the case if we started tracing from the light sources and wouldn't know which pixels the ray ends up. In that case, every thread would need a separate block for the whole image, but the rest works the same. We can still add up the blocks for the whole images after the thread finishes. And finally, we normalize. Rendering is very easy to parallelize, even to multiple machines. This works by computing multiple images with different random seeds. They can be added up after finishing rendering using 32-bit floating point image formats. That way, I occupied several thousand CPUs and more than a terabyte of RAM during my master thesis at Aalto, Finland. Some bottlenecks start to appear once your scenes become very large, for instance in large film productions. Sometimes the scenes don't even fit into RAM anymore, and special architectures need to be employed. That was a short section about parallelization. Many renderers implement threading by rendering in blocks. These blocks need to include a small border to account for filtering. And it is relatively easy to parallelize even to multiple machines. The next topic is measuring error. And I know that it is a bit boring, but it's important nonetheless. It is crucial to be able to compare algorithms, but we can do even more, as we will see. The picture shows a former eucalyptus forest in Australia. The error there was to put koalas in the trees. Too many koalas and too few trees and of the wrong type. So, estimators. Well, they estimate values. For instance, the color of a pixel. As such, they don't give the real value, and therefore there is a certain error. Estimators are denoted with a hat. This is a general statistician thing. And the error can be computed by subtracting the real value from the estimated value. This is the absolute error, opposed to the relative error that we can see in here, which is divided by the real value in addition. So this error is relative to the real value. The absolute error in here is signed. There is also the amplitude of the error, which is the same thing, but the absolute value is taken. The nomenclature is a bit fuzzy in here. Sometimes this is called absolute error and sometimes this. When we want to compute the error for the whole image, we can take the mean of all errors. But in that case, we need to compute the amplitude error, or even better, the square of the error. Otherwise, the positive and negative errors would cancel out. The real value I is usually not available. Therefore, high-quality reference estimates, also called ground truth, are used. We will now see some examples of such errors. On the left, you see a high-quality reference, and on the right, the absolute error of a path tracing algorithm. And you can see that there is a lot of error in here and in here. In here, you can get an idea of the difference between absolute and relative error. The error shown is not the error of a single rendering, as we saw in the previous slide, but the standard deviation per pixel. This is something that we will get into in the next few slides. But you can see the difference anyways. In the first example on the left, it seems at first that the relative error is better, because in very bright areas like here and here, the error does not matter as much because we will not see it anyways. But on the right side, we can see that the error can become very large in dark areas. In fact, it's needed to add an epsilon to the reference so that it doesn't produce division by zero errors. But enough of that. Let's now look at classes of errors. On the right, you see plots of signed error, so that's the estimator I minus the real value I, against the number of samples on the x-axis. You won't see such plots in papers or websites, as other error measures are used most of the time. But they are good for visualizing the concepts here. Unbiased estimators, like for instance Monte Carlo integration methods, have the expectation of the estimators equal to the real value. The error plot of a single estimate oscillates around the zero value, and the amplitudes become smaller as n increases. Biased but consistent estimators at no point have the expectation of the true result, but the error becomes smaller with larger sample sizes. The estimator converges to the ground truth, as we can see in here and in here. The error can be negative as well. This here is just an example. And finally, there are biased algorithms that never converge to the true solution. That usually happens when you trade noise for bias. You can get a nicer picture with less noise that doesn't match the physics of light, for instance. A typical example would be clamping the contribution, clamping fireflies as you saw them in the first part of the path tracing lecture, limiting the recursion depth, or just not render certain effects, like for instance avoiding to render caustics. We are focusing on unbiased Monte Carlo integration, and at this point I would like to make a super brief recap. I is the integral of f over the domain D. We can multiply f by p over p in here, which is 1, and turn that into an expectation, where the samples are taken according to a probability density function of p. That is not an estimator, as we have no procedure to estimate yet, but we can use the law of large numbers to turn that into an estimator. The law of large numbers tells us that the average of a ever-increasing number of samples x is the expectation. When we apply that to our stochastic variable f over p, we get the Monte Carlo estimator, which you see in here. Now we need another super short recap about probability, and the variance in particular. The variance of a stochastic variable gives us a measure of how far spread out the samples will be. And you see two equivalent methods to compute the variance. The next result tells us how the variance of a constant times an uncorrelated variable x is computed. The constant can be squared and moved out, and the variance of a sum is the same as the sum of the variances. These equations are taken from Wikipedia. Finally, the central limit theorem. It is usually written in a slightly different way, but this form is equivalent and more useful to us. The average of a ever-increasing number of samples of a stochastic variable x tends towards a normal distribution with expectation given here and variance given here. I've put the central limit theorem and our estimator next to each other in here. We see that the estimator is pretty close to the central limit theorem with stochastic variable f over p. That means that in the limit our estimator I hat, which is actually also a stochastic variable, becomes normal distributed. So if we would draw many samples of this I hat with a very large n, the results would match the normal distribution. Now let's look at the error I hat minus I. We know that the expectation of I hat is I, and so we can substitute it. Now we quickly see that the expectation of the error is 0. That's logical, since it is unbiased. We can also look at the variance of the error. We saw that the variance of a sum of stochastic variable is the sum of variances. So we can fill in, and the variance of an expectation is 0, so therefore the variance of the error is equal to the variance of the estimator. And finally, now without steps, the distribution of the error also tends towards a normal distribution. You should be able to check that without problems on your own. Okay, the variance of the estimator is important. What can we find out about it? On top, we see the estimator again. And as said, estimation is a stochastic process, and therefore the result is a stochastic variable again. We can compute the variance of that estimator. The result will tell us how far spread out the estimates will be. That means if we run the estimator several times, how far spread out the results will be. At the same time, how far spread out the error will be. Using the equation from the probability primer before, we can pull out the 1 over n, like we see here, and make this a sum of variances. Now, the variance of f over p is a constant. It's a theoretical one, we don't know it, but we know that it exists. And the sum of n values, of n constants, is n times that value. So we can replace the sum by n. And 2 of the n cancel each other out. So the result here is that the variance of the estimator and the error is 1 over n times the variance of a single sample. Neat. To summarize, the distribution of error of a Monte Carlo estimator tends towards a normal distribution as n increases. Its expectation is 0. Yes, because it's unbiased. The variance of the estimator is also the variance of the error. And finally, the variance is in strict relation with the number of samples. Double n will result in half the variance. Variance. What do we know about it? Can we compute it somehow? Maybe. Let's take a look. We heard about importance sampling before, and we learned that it can be used to reduce the variance or the error. It would be even better with multiple importance sampling. But can we compute the variance out of it? Well, no. Or at least I'm not aware of a method to do that. It's kinda a dead end. One of our researchers is working on a method to use the information gathered by the path samples to get a better estimate of the variance, but that is only an improvement to what we will see now. We can measure the sample variance. It's simple. You have a bunch of values of samples, these f over p's, and we can compute the variance of it. In order to get an estimate of the estimator variance, we need to divide by n, so division by n squared in total. This process does not even require a reference solution. It is even possible to do that online, which means that we do not need to compute the average of all samples before we compute the variance. Search for the Welford algorithm. When we want to do that for path tracing, we would compute the per pixel variance. Time for some examples. On the left, you see a rendering of a bathroom scene. On the right, there is the standard deviation per pixel. In my opinion, the standard deviation is preferable because of the linear scaling, while variance has a quadratic scaling. Here you see another example, and we can clearly identify that the caustic is problematic for the path tracing algorithm due to the high standard deviation. Alright, what can we do with that information? One thing, we know that the error in that area is large. But we also know that doubling the number of samples reduces the estimator variance by half. So throw more samples at this problematic area. This is called adaptive sampling, and there are many methods to do that in intelligent ways, but that would be too much for this lecture. Look for papers on your own. Another method to combat noise in rendering is smoothing. Adaptive smoothing is very often used, so we don't want to blur edges, for instance. These methods are biased, however, but a little bias is often better than a noisy image. If we know that there is a lot of error in a certain part, in other words, objectionable noise, we can apply more smoothing. And finally, we can compare different algorithms. On the left we see path tracing. It contains a lot of error in the caustic. Bidirectional path tracing on the right shows less error in these caustics, but it seems that there is more error inside the refractions of that bottle. So generally, if you develop a new algorithm, it is good to know its strengths and weaknesses, and this is a good method to do that. In my opinion, this method is better than computing the absolute error of particular renderings as we saw in the intro. Finally, and now for real, we often want to rank algorithms. For example, say algorithm A is better than algorithm B according to some metric. Literature often uses mean square error to do that. That is, per pixel mean of the squared error between a rendering and a ground truth. There are many variations of that, for instance computing the error relative to the brightness of the reference, or computing mean absolute error, which weighs outliers less, or computing root mean square error, which is linear like standard deviation. All these methods are sensitive to outliers, fireflies in the case of path tracing. That I've tried to visualize in here, where we have the number of samples or the rendering time on the x-axis and the error on the y-axis. This is a logarithmic plot, and as we have learned, the error should go down with time. And if we have no outliers, these lines should be smooth. However, the jumps are outliers, and so it would be hard to choose a fair rendering time for comparison. So, for comparisons, I'm advocating to use the root of mean variance, where the variance is estimated per pixel. Here are some reading links. The first one is a diploma thesis and the second one a paper. Both roughly cover the same methods, which also includes a plot of error over frequencies, which you can see on the bottom left, but the first one is much more extensive. And here comes the summary slide. We have our mission accomplished. We now know how to judge the quality of our rendering work. For unbiased algorithms, like path tracing, that is simply measuring the variance or standard deviation. We can use that knowledge to throw more samples at problematic areas, smooth out noise specifically in problematic areas, or simply compare rendering and sampling strategies. That here in the background is my cherry tree in Poland. But we'll look at post-processing now. That is, what do we do before storing or showing our computed radiance values? Let's start with a bit of context. The first thing to realize is that the dynamic range of light in the real world is considerably larger than what we can show on displays or store in normal image files. Take for instance the difference between illuminating a piece of black and white paper by the sun versus the moon, in here. The sun's illumination is 80 million times stronger. The human vision system can adapt and process a difference of up to 100 million. Adaptation takes some time, but still. In technology, displays can have a difference between the brightest and the darkest pixel in the ballpark of thousands. Modern displays that can partly dim their backlight can do more, but that requires special drivers and especially authored content. The default of storing images is 8 bits per color channel, and that gives us 256 levels of brightness. This seems almost archaic, but that's the deal for most cases. Our computations during the light simulation use 32-bit float, and the range should be enough. So, tone mapping is about reducing the dynamic range from our light simulation to a 0 to 1 range that can then be mapped to an 8-bit integer. We need to compress the range. And on a side note, there are 10 or even 12-bit displays today, but these require different processing that probably happens in a special software or in the driver anyway, and we will not cover it. It is easy to output 16 or 42 linear floating point data for that purpose. Let's take this image as an example. It is tone mapped in some way. For the sake of the argument, let's assume that the light in here, right here, has a brightness of 35.5. That's just an example, but the important part is that it's a floating point value that could arise from rendering. On that white piece of paper, let's assume that we have a brightness of, say, 1.2. And somewhere here in the background, let's say it could be 0.1. How to map that range to something between 0 and 1 so that we can then convert it to 8-bit. One option could be to divide by the largest brightness value. That is actually a valid method, and don't laugh, I used it at some point in time. If the scene has a low dynamic range, that is pretty okay, but it's certainly not a good method in terms of quality and stability. Our next attempt could be to clamp the image to a range of 0 to 1. That is what often happens before tone mapping is implemented. With most scenes, that is not that bad either. In here, again, it shows some instability. Taking the logarithm is a very basic tone mapper. I use it to display some scientific data in another domain. It's simple, but not really proper. We would like to adjust the parameters, give more light to the shadows, etc. And right here, we now have a proper tone mapper, Reinhardt. Before we continue, let me say that there are global and local tone mapping algorithms. The global ones apply the same function to all of the pixels, while the local ones are applying different parameterizations depending on the local neighborhood of a pixel. Accordingly, the local ones are slower, but they can retain more details. We'll see an example in 2 slides. The Reinhardt tone mapper is widely used, and there is a global and a local variant. We will not cover the processing steps, it would be tedious and you would have to look them up when you implement it anyways. Refer to the paper. The goal of that process is to find a transfer function, like you can see an example over here. The exact shape of that function depends on the whole image in case of the global variant and on the local neighborhood in case of the local variant. That shape is somewhat similar to a logarithm. Hence, logarithms are also usable, as we have seen before. Let's now look at some examples. On the left, you can see a global mapping and on the right, a local one. If you look closely, you can see that some of the darker areas on the right, like for instance in here, are darker compared to the left. The window in the roof in here is a bit blurred. There is some sort of bloom. Here on the right, it's much crispier. Let's zoom in a bit. The global variant, again on the left, is less crisp than the right one. Look here at the arches and the saints. They are a bit washed out on the left compared to the right. And again, the darker parts of these wooden beams are darker here compared to here. Reinhardt is not the only tone mapper. Here is a reading list, but there are more on Wikipedia. Enough of tone mappers. Let's turn our attention to gamma encoding, something slightly different. A human perception of brightness follows an approximate power function. There is greater sensitivity to relative differences between darker tones. Therefore, gamma encoding is used to optimize the usage of bits when storing or transmitting an image. So you want to give more bits to darker tones, because we can distinguish them better. It's applied after tone mapping, and the equation is the image to the power of 1 over 2.2. This factor 2.2 is sometimes 2.3 or something. It depends on the operating system and some other things. Check the net for more information. But the crucial part here is that it is applied after tone mapping, first, and second, when you read textures, you sometimes will need to decode gamma, because in the light simulation we use linear intensities, and many image formats for textures also store the image data gamma encoded. Therefore, we need to decode the gamma. To sum up, the mission of post-processing is to find good methods to massage the data before storing or displaying it. Tone mapping is used to map from high dynamic range to a 0 to 1 floating point range, and gamma encoding is used for storage. These two things are not needed when we use HDR formats because they store their data in more bits and as floating points, so they can also store, for instance, 35.5. Alright, that's it for today. We covered filtering, parallelization, measuring error, and post-processing. Oh, and I wanted to include that image in my diploma thesis, a glass of water with some oat drink, which shows participating media in that water, and a nice caustic in here. That leads us to the topic for the next lecture, materials. You will learn about how to model the surface of that wooden table, how to compute the reflection from the glass and the water, and I don't remember, maybe also briefly about participating media. Okay, thanks for your attention. See you next time.